Hello! In the previous video, we learned how to solve quadratic equations by factoring. We saw that factoring is very fast when it does work, but we can't always figure out the right factors. Now we're going to talk about a method that always works, but the problem is it's a little bit technical and takes some time. So there's a trade-off between speed and actually getting to a solution. So the method is called completing the square. Now, I'd like to remind you just how we square a binomial. If you've got something like x plus 2 and you square it, that x plus q is in brackets, you get x squared plus 2qx plus q squared. If you FOILed it out and combined your like terms, you'd see that's exactly what you always get. Now, my grade 11 teacher gave me a little rhyme. She said, when you're squaring a binomial, you square the first, square the last, double the product, ooh, what a blast. Now, we are going to be making use of this idea as the key machine in completing the square. We're going to look for structures exactly like what we have on the right-hand side here and replace them with perfect squares. So a little bit backwards to the way you may normally use this, but that's our objective. Take a three-term quadratic and replace it with a perfect square. In fact, in general, if we want to complete a square, what we mean is we take a quadratic expression and we rewrite it as a real number times a perfect square plus a constant. And it turns out every single quadratic expression can be rewritten like that. Now, why is that helpful? Well, it allows us to solve any quadratic equation we could ever come across. That's number one. Number two is that it allows us to draw the graph of any quadratic function. We're certainly going to do that later in the week. And there are also some uses for it in your further math courses. So let's see how it works. If I take a look at this simple example here that has a quadratic coefficient of 1, I can take a look at my linear coefficient here. I see it's -6. And if I look back up at my format for squaring a binomial, I notice that I have this 2q as my linear coefficient. What does that mean? My linear coefficient is -6. What's the value of q? Well, 2 times -3 is -6. q is -3 in this scenario. So I'll just rewrite my expression as x squared plus 2 times -3x. So I haven't really changed anything, just the look, but not the essence. And now I'd really like that plus q squared to appear, plus -3 squared. I'd like a plus 9 to be there. Unfortunately, we have a plus 11. How are we going to deal with that? Well, we're going to kind of be pretty sneaky here. We're just going to add it. We're going to add exactly the thing we want. But of course, in expression, you can never do that. You can never just add a term for absolutely no reason, okay, and without paying some kind of cost. So we're going to remove it right away. Now, you may be saying to yourself, we haven't done anything. And you're kind of right. But what can we do now? We can just repackage all this stuff. The first three terms we can break down according to our rule at the top. Look at the red here. We have exactly that structure. It means we can replace it with the left-hand side of that. So the first three terms there can be replaced with x minus 3 all squared. Now, what remains? These two terms out here. They don't just disappear, they're part of our completed square. But notice they're just constants, so we can figure them out, add them together, and get our final constant. So we've got -9 plus 11, and here's our completed square, x minus 3 all squared plus 2. So there we've done it. We've rewritten our quadratic expression as a real number, I guess it's 1, times a perfect square, x minus 3 squared, plus a constant, plus 2. So that's the method of completing square. Our objective is to rewrite our quadratic in that form. Let's try another example. Here now we have a quadratic coefficient that isn't 1. So, in this case, we'll factor it out of the first two terms at the beginning. The quadratic and the linear term. Now, again, inside those brackets there, I'm going to want that square the first, square the last, double the product, ooh, what a blast, format to show up. So I need to figure out what my q value is. So if I look at the linear expression there, and my linear coefficient being 3, I think to myself, 2 times what number is going to give me 3? Well, You may not like this answer, but the answer is definitely 3/2. Okay? Essentially, you can just divide the linear coefficient by 2 to always find your q value. So, what's the next term I definitely want to show up? Well, plus a 3/2 squared. Then it fits that format from the last page. But that plus 3/2 squared can't just come from nowhere. I need to take it away right away. And then, of course, I still have my minus 7. Now, in these brackets, these first 3 terms can collapse down. They're exactly the structure I want. They can collapse down into that perfect square, x plus 3/2 all squared. Now I have another constant left over inside those brackets, so negative 3/2 squared is negative 9/4. And I'd like to combine together the negative 9/4 with the negative 7, but they're in different layers of brackets, so we need to expand out the outermost brackets first, distribute the 2 into both terms. So what do I get? I get 2 times my perfect square. Now negative 9/4 times 2, you can check this for yourself, is negative 9/2. And now we've got minus 7. Now wait a second. Why would I write negative 7? I want to add it to 9/2, so let's write it as 14/2 right away, because I need a common denominator. And lastly, I've got my completed square. So here we see we have exactly the completed square structure. We've got some real number times a perfect square plus a constant. And there we go. Now, how can we make use of this to actually solve an equation? Well, notice, let's just take a look back at what we've done. Here I had an expression at the top that had 2 different terms involving x. It was nice and simple. But my bottom, my final expression that it's equivalent to, it looks a lot more complicated, but there's one really nice property it has. It only has 1 term involving x in it, right here. So we've taken an expression that has multiple instances of x and rewritten it as an expression that has only 1 instance of x. That means we could isolate x if we wanted to, if we were trying to solve an equation. So if I want to solve a quadratic equation by completing the square, I'll bring all the terms to the left-hand side so that my right-hand side is 0. So that's step number 1 there. Then I'll complete the square on the left-hand side, so now my left-hand side has only 1 x in it. And then I can isolate that x. So let's see how this works. I've got my quadratic equation here. Step 1 is to bring all my terms over to one side. So the right-hand side is 0. Now I'll complete the square on the left-hand side there. So negative 7 is negative 7/2 times 2. So I want plus a negative 7/2 squared to show up, but I have to take it away right away. And of course, I've still got my minus 2. Now the first 3 terms, just like we saw, are going to collapse down into x minus 7/2 squared. Then I've got, minus 49/4. And then minus 8, but let's write it as a number of quarters just to save ourselves some time. Minus 8/4, because we know we need to combine those 2 constants. And so we've got x minus 7/2 squared minus 57/4 is equal to 0. And we finished completing the square there. That's great news. So now our next phase is to isolate that x. Notice there's only 1 x showing up there. So we can go ahead and isolate it. So we'll start off, we'll peel away the outermost layer, this negative 57/4 there. So we'll move it over to the right-hand side. We've got x minus 7/2 squared is equal to 57/4. Okay. Then after that, we'll peel away the next outermost layer that's around the x. So we've got that square. Well, how do we undo a square? Well, we'll take the square root of both sides. Actually, we'll need to take the positive and negative square root of both sides, because I don't know which one was being used here. There are two possibilities. The positive square root or the negative square root squared will give me 57 over 4. And then the last thing that I need to do is just add 7/2 to both sides. And I just can't help myself. I'm going to rewrite root 57 over 4 as root 57 over the root of 4, which is 2. So there we have our completed square helping us solve a quadratic equation. Now this method will solve any quadratic equation you'd like, but notice there are a lot of steps to it. So we have quite a bit of work to do. It takes a fair bit of time. Let's try maybe one more example here. How about we look at number 3 there. So let's bring everything over to the left-hand side. We get 2y squared plus 4y minus 12 is equal to 0. And now I'll factor a 2 out of the first two terms. And then I'll look at what's inside my brackets. And I'll say, okay, 2 is 2 times what? Well, it's 2 times 1. So I'll add a 1 squared and subtract a 1 squared inside those brackets. And now we've got, we can collapse down our first three terms there into y plus 1 all squared. But of course we still have this little constant hanging around. It's a minus 1. And I'd like to combine it somehow with that negative 12 on the outside, so let's distribute the 2 into the two terms in brackets there. So we've got 2 times y plus 1 squared minus 14 is equal to 0. So we've completed the square. We've got only one instance of our variable y showing up now. All we have to do is isolate y. So we'll peel away the outermost layer. We'll add 14 to both sides of the equation and move over that 14. Then the next outermost layer is the 2. So we'll divide both sides by 2. Then we'll take the positive and negative square root of both sides. And finally, we'll subtract 1 from both sides. Okay. And we found our two solutions to that quadratic equation. Either y is negative 1 plus root 7, or y is negative 1 minus root 7. Please finish that example number 2 for yourself and make sure you completely understand this idea.